Hello, everyone, and welcome to our last subtopic of angles and angle measures, which is linear speed and angular speed. Now, you may be thinking, though, why do we need to discuss linear speed and angular speed? Well, here's the reason. It is actually one of the real-life applications of the length of the circular arc and angles. All right? So, let's just say you have a circle. All right? This circle represents the distance you travel. All right. You start from here, then you end here. So that's the start and that's the finish. All right. So here we can actually see that it's like a circle, but you know, in reality, uh, that's basically how you move. You get me? It's like what I'm trying to imply here is that the way how you travel, you know, represents the circle itself. Right? So here, from this point up to there, you form an angle. All right. So now, what would be the distance between the start and the finish? So this is actually an arc length. You get me? So you're going to use this formula. All right. So it shows the application of the circular arc. And of course, with a given angle, it already implies that it is applied with the lesson we learned about angles. So we learned before about degrees and radians, the length of the circular arc. These two are applied in the linear speed and angular speed. All right. So now speaking of speed though, since you travel from the starting up to the finishing line or finishing point, I mean, how fast does it take you from there? From here to there, how fast does it take you from there? Like, is it that fast enough? Like, let's just say the way how you reach from here up to there is the same average speed of a car, or I mean, a regular car, I mean. Do you understand? Like, okay, you form an angle from start to finish. Now, how fast did it form? Especially the distance, how fast you come from here up to there. So that's where linear speed and angular speed comes. All right. They are actually related to physics, which is circular motion. In here, you'll be learning a topic that is actually part of circular motion. All right, which makes sense because you see in our previous examples, right, we basically have a problem, a real life problem that's related to the length of the circular arc, right? Like, for example, okay, this is the starting and this is the finish. Okay, then you have an angle. Now, find the distance here, all right, from start to finish. You see, the way how it moves is in a circular path. Therefore, it is related to the circular motion, all right? And according to Math is Fun, ah, sorry, according to Coral in website, I think Math Libritex, if I'm correct, according to him, circular motion can be studied using radian measure and arc length. So this already gave you the idea that what we learned before about angles and arc length is applied to circular motion. It applied to circular motion. Okay? So now let's have some examples of circular motion. Like this guy right here, he has an object, all right? It rotates from this up to, actually not up to, but basically it rotates in a circular path. You get me? Like it just rotates with this object. Then here we have a station that makes you revolve around the station in a circular path. So you're going to revolve. All right. By the way, if you're asking me, what's the difference between rotation and revolution? When you say rotation, it's basically you're going to move your body, but in a how should I say this in your stationary position. So for example, This is your body. Then your face is facing the right. Then you, let's just say, rotate up here counterclockwise. So your face is directly looking at this path. You get what I mean, right? You get what I mean? Basically, you rotate yourself in a stationary position, like you move yourself in a stationary position. But if you're talking about revolution, that means if this is uh, a given point and this is you, you move around that point. So this is what you call revolution. This one, moving yourself, is a rotation. This one, on the other hand, revolution, because you move around the object or point in a circular path. And last but not the least, we have a cyclist. If this cyclist goes in a circular path, then that would be also a great example of circular motion. However, this cyclist is just going on this direction. So it's unclear at what direction he's going. But what is already clear for us is that the tires are rotating. So this is also applied with the circular motion. All right. So now let's have the, oh, wait a minute. Anyways, sorry. So let's now have the idea of linear speed and angular speed. Let's start first with the linear speed. Let's just say you have a yellow ball that goes on a circular path. Or I think it would be better if we say that it rotates, or let's just say it revolves around the center of the circle, like it goes around the center. Now, here's the thing. Suppose a yellow ball moves in a circular path. Which direction is it going? Well, if you're going to think about it, well, yeah, it basically goes, where does it go? Well, so it implies that if example, the rotation is in counterclockwise, so from here up to there, that means that the direction will just basically follow the circular path. So from here up to here and there. That's it. Well, if that's what you think, then you're wrong. All right. In reality, yes, you do have a point. It moves in a circular path, but the direction is always straight. Why straight though? It always follow the straight path, or maybe direction, or yeah, I think you get my point. It always follow the straight path that is perpendicular to the radius of a circle. So I said that this ball is revolving around the object in a counterclockwise, right? So let's just say the ball is here. All right, this is the let's just say final position. All right, the ball is here. Okay, and these lines are the radius. Okay, so if it rotates in a counterclockwise, okay, expect that the direction would be perpendicular to the radius of a circle. So that means it goes from here. Okay, from here to there. All right. So if the ball is here, that means the direction would be like this. Okay. So if the ball is here, then the direction would be like this. All right. But what if it's not in a counterclockwise, but rather it's clockwise? Then that would be different. So if it's clockwise, meaning it moves like this, so that means the direction is from here to there, you know. And if the ball is here, then it moves from here to there. And similarly here to there. You see, it follows a straight path that is perpendicular to the circle. Think of it this way. Let's just say this is you, all right? You have a slingshot, but that slingshot is not those slingshots that you know now, all right? Rather, it is a slingshot that consists of a rope and a ball. And you're planning to hit an object that is on the table, all right? You're not going to throw the ball with your hands. All right, you're not going to destroy this object, this object right here, with the use of the ball by hitting it, or by by just using your hands or body to destroy this one. Rather, what you're going to do is you're going to use the rope to make the circle go hit the object. The question is how? Well, of course, you're going to rotate it, right? You're going to rotate it in a counterclockwise, all right? Then, once it's already, let's just say, it's fast enough that the ball around it is actually going faster. When you release it, it will go in a straight path. You get me? It will go in a straight path. So that's what actually other people do when they're hiking. Like when they have a rope and then there's like, I don't know. Actually, let's just say this is a rope and then there's like a hook. There's like a hook. When there's like a cliff around the, let's just say, around the walls of the mountain, they use that. They use that hook. Then they're going to rotate it. Then they're going to reach it to the cliff uh so that the hook will stay down that cliff, and you're going to climb up there until you reach that cliff. You get me? So similarly here, if you're going to rotate the ball as fast enough, then when you're going to release it, it will go to the straight path, hitting that ball. That is why it is in a what? It is in a straight path. The direction should be perpendicular to the radius. And yes, it is based on the rotation, of course. It is based on the rotation, but the direction is always straight. All right? So now we want to find the speed by the yellow ball. Like from, let's just say from here, from here going here. What will be the formula? So we're going to talk about that next time.